So in this question here, we've got a three-dimensional linear transformation, which is given as this one here: 3x plus 2y plus 4z, 2x plus 2z, and 4x plus 2y plus 3z. There are x, y, and z components. Now, with that linear transformation, we want to try and find the eigenvalues and the eigenvectors. Now, first of all, you need to find the eigenvalues before you find the eigenvectors. So the way I'm going to do this is, first of all, turn this linear transformation into a matrix. So I'm going to call that matrix A. So that equals, if I take these individual components and go x, y, and z and go from there. So my coefficients here are 3, 2, and 4. 3, 2, and 4. Then I've got 2. There's no y component, so I put a 0. So I put 2, 0, 2. And for the last part, 4, 2, and 3. 4, 2, and 3. So that's my matrix A. Now, to find the eigenvalues, I need to use something called the characteristic equation. And what that consists of is the determinant of, now what I use here now is something called the identity matrix, which I'm going to just write down for you. So it's A minus lambda, so that's some constant, and multiply that by the identity matrix. Now the identity matrix, so here we're dealing with a 3 by 3 matrix, so we need a 3 by 3 identity matrix. So that what that has is just 1 in all the diagonals and then 0 for all the other terms. So I've got 1, 0, 0, 0, 1, 0, 0, 0, 1. So that's the identity matrix. And what I need to do is to multiply that by lambda. Okay, so let's go about finding that. So now we want the determinant of A, which is this one here, 3, 2, 4, 2, 0, 2, 4, 2, 3, and minus lambda times this, which is 1, 0, 0, 0, 1, 0, 0, 0, 1. And then what we do, this determinant here, we set it to be 0 and then solve for lambda. So this now becomes 0, and we set this matrix also to 0. Okay, right, let's put a bracket around all of that. Okay, well, multiplying this by lambda, all the 1's become lambda, and then the 0's just stay as 0. So now we want the determinant of this one here, 3, 2, 4, 2, 0, 2, 4, 2, 3, minus, and then we just put lambda in where there's a 1. So that becomes like that. Okay, and then it's still set to 0. Okay, so now determinant of A minus lambda I. So now we've got determinant of that will be, now just go just to one matrix, because subtracting one matrix from another is just each individual component subtracted individually. So 3 minus lambda, 2 minus 0, 4 minus 0, so they just stay as they are. And then I've got 2 minus 0, 0 minus lambda becomes minus lambda and 2. So 2 minus lambda and 2. Then here the 4 and the 2 will stay, and I'll have 3 minus lambda. So that's my A minus lambda I bit. And then we still set that to be 0. Okay, now the important thing is trying to find the determinant of this 3 by 3 matrix. So what I'm going to do is now I'm going to take this off the board, write this matrix up here, and then we're going to find just the determinant of this on its own. Then after that we'll set it to 0 and try and solve for lambda. Okay, so now I've got it set up like this. So first of all, I'm just going to concentrate on this determinant. Now the determinant of a 3 by 3 matrix, if you check the link below, I'll show you how we do that in more detail. But for this video, as we're doing eigenvalues and eigenvectors, I'm just going to run through it a little bit quicker. So we take the top row, 3 minus lambda, just take each individual determinant on its own, and then we multiply that one there by the determinant of this bottom corner here, this little 2 by 2 here. So we want 3 minus lambda and we multiply that by the determinant of minus lambda, 2, 2 and 3 minus lambda. And then we subtract it with 2 times the determinant of the next 2 by 2 matrix. So if we use this one, we make a 2 by 2 out of these ones. So we have 2, 2, 4, 3 minus lambda, and then we add 4 times the determinant of this 2 by 2 matrix here. So now I've got 2 minus lambda, 4 and 2. Okay, right, let's run through that. So let's take the determinant of this one. So remember, it's AD minus BC. So minus lambda times 3 minus lambda. So let's put that in there. Minus lambda times 3 minus lambda. And subtract this one here. So 2 times 2 is 4. So I'm just going to put minus 4. And then all of that is multiplied by this 3 minus lambda. And then the next one, minus 2 times. Okay, let's take the determinant of this one. So 2 times 3 minus lambda, that's going to be 6 minus 2 lambda. And here, subtracting the other diagonals, 2 times 4 is 8, so subtract 8. Okay, and then 4 times, so determinant of this, 2 2s are 4, that's fine. 4 times minus lambda is minus 4 lambda, but then subtract it, that's going to give me plus 4 lambda. Okay, right, now let's just simplify this off a little bit. So I've put this one with different kind of brackets, just so as we can see what's going on, because this is the trickiest part, and multiplying by this is where most of the mistakes are going to occur. So let's simplify the inside of these square braces. So minus lambda times these two is going to give me minus 3 lambda plus lambda squared, and then minus lambda on its own, that's fine, so minus 4. Okay, now 3 minus lambda multiplied by all this, let's multiply all of these by 3. So now I've got minus 9 lambda plus 3 lambda squared, and 3 times minus 4 is minus 12. So that takes care of that. And then minus lambda through all of these. So now I'm going to get plus 3 lambda squared minus lambda cubed and plus 4 lambda. So 6 terms. Okay, so we know we got to the end of that one. This one here, minus 2 lambda, 6 minus 8 is minus 2. So minus 2 lambda minus 2. So now we need to multiply all of that by this minus 2 here. So minus 2 times minus 2 lambda is plus 4 lambda. And minus 2 times minus 2 plus 4. So that's straightforward. And now multiply by 4 with all of these. So now I'm going to add 16 plus 16 lambda. Okay, so that's a lot of terms. Let's simplify it off and put the like ones together. So there's only one cube, so minus lambda cubed. Now squared terms should be 2. So 3 lambda squared and 3 lambda squared. Add that up, 6 lambda squared. Okay, right, now the lambda terms. So we've got minus 9, we've got a plus 4 and a plus 4 and a plus 16. So 16, 20, 24, minus 9, plus 15. So plus 15 lambda, and then the constant of which there should be a couple. 16 minus 12, that gives me plus 4, and plus 4 gives me 8. So there's 3 altogether, in fact. So plus 8. And then remember, we set this to 0. Okay, so now we need to solve for this. Now if I multiply through by minus 1, I could have lambda cubed minus 6 lambda squared minus 15 lambda minus 8 equals 0. Now if you check the link below, we solved this in a separate video, so I didn't want to do that in this video because this is quite a lengthy video as it is with these two questions. And we solved this, and what we got was lambda plus 1 squared times by lambda minus 8. So that then gives us our eigenvalues, which are the solutions to this, which gives us lambda minus 1 twice. So lambda minus equals minus 1. That's multiplicity of 2. And lambda minus 8, solving that, lambda equals 8. So then obviously just a multiplicity of 1. So that's the solutions there of that to give us our eigenvalues. Now we need to use those and find our eigenvectors. So that's going to be next. So I'm going to clear the board and then we're going to go into that. Okay, so now we can find the eigenvectors. Now I've written here the equation to find the eigenvectors. So we take this matrix here, multiply it by the standard vector x, y and z as its 3 dimensions and set it to be 0. And then we get a system of equations and we find the solutions for x, y and z. So we take this matrix here. So let's just write it down here quick. 3 minus lambda, 2 and 4. 2 minus lambda, 2, 4, 2, 3 minus lambda. Multiply that by the standard x, y and z and set them all to be 0. And then we solve the equations. So what we do now, plug in lambda equals minus 1 to start with. You can start with 8 if you wanted, it doesn't matter which way you go. But if lambda equals minus 1, plug that in here and we'll get some sort of equation. So 3 minus minus 1 will give me 4. Multiply that by x. Then I've got 2 times y, so plus 2y. And then 4 times z. And that will be 0. So now lambda here is minus 1, so that becomes plus 1. So I've got 2x, 1y and 2z. 2x plus y plus 2z. And again that's set to 0. And this time I've got 4 there. So I've got 4x, 2y and 4z. 4x plus 2y plus 4z equals 0. And now we need to solve these equations. So I'm going to write them up here to start with. So these are all of the same order here. So I'm going to write 2x plus y plus 2z equals 0. So that's my first equations there. I need to solve for my x, y and z. So now what happens when lambda equals 8? So clear this off the board and I'm going to go through it when lambda equals 8. Okay, let's plug lambda equals 8 into this. So now 3 minus 8 is minus 5. So minus 5x plus 2y plus 4z. And that's set to 0. Same here. This time I'm going to have minus 8 in here. So I'll have 2x minus 8y plus 2z equals 0. And this time again, I'm going to have a minus 5 again there. So now I'm going to have 4x plus 2y minus 5z equals 0. Okay, let's have a look at this. Now, what I did in the previous video was I solved this system of equations and this system of equations using Gauss-Jordan elimination. And the results we got for when lambda equals 8, my results of that were 2k, k and 2k. That was my solutions for this. So for example, if I plugged in 2 for x, 1 for y and 2 for z, I should get these all to be true. So for example, minus 10 plus 2 plus 8 will give me 0. Same here, 4 plus minus 8, that's minus 4, plus 4 sets to 0. And same here, 4 times 2 is 8, plus 2, which is 10, and then minus 10 again, sets to 0. So that we know that's a good result for that one. And then when we, for the lambda equals minus 1, we had 2 results. So we got minus k, 2k and 0. And we also had minus 2k, 0 and 2k. So that was for when lambda equals minus 1. So just make a note of that one there. So for example, if I plugged minus 1 for x, I get minus 2 plus 2y, that gives me plus 2. So minus 2 plus 2 is 0, and leave that as 0, that comes to 0. And same here, if I plug in -2, so -2 for x, I'm going to get -4, 0 for the y, and 2 times 2 is 4, so that's going to give me -4 plus 4 gives me 0 as well. So these system of equations work. So these are the results of my eigenvectors. That's for lambda equals 8. And these are the results for my eigenvectors when lambda equals -1. So check out the link below on how we did the Gauss-Jordan elimination. But that's the result of this question here. Okay.